Hey folks, hope you're keeping well. So in the last video I'd done, we looked at free radical substitution reaction mechanisms. So we looked at the three important steps that were involved in it. We had a look at what radicals were and sort of how they wreaked havoc. And if you haven't seen that video, I'm going to put a very fancy link that you click into up here. And then you can dive into this. So this video is going to serve as like a part 2. So we're going to take that reaction and we're going to apply it to a very familiar problem, which is how holes are created in the ozone. And so these holes that form in the ozone we sort of refer to as ozone depletion. And this ozone depletion is actually caused by free radical substitution reaction mechanisms. That chlorine radical is wreaking havoc again, pretty much. So we're going to look at that. So what's the plan for today? So more or less, we're going to look at one MCQ. The reason why it's just the one, I am going to break it down. But also at the very end here, I'm going to look at a good handful of past exam paper questions. So I think we can get away with just doing one at the start. I'm then going to look at CFCs, chlorofluorocarbons. These are the bad boys responsible for producing that chlorine radical. So we're going to look at the CFC uses in the past. They were very popular. And then after that, we're going to discuss UV light and how the ozone protects it. We'll move on to the ozone depletion reaction mechanism, that also important reaction. And again, if you have looked at the video before this and you've tried a few questions, you're going to fly through this. It's the exact same thing with different reactants and products, exact same steps. So after this, then we're going to move on. So the nitrogen oxide effect on oxygen, it's not a popular question, but it has been asked and it does be asked. So we're going to look at that. And again, it's a free radical substitution reaction. Nitrogen oxide is another element, not just the chlorine radical. Nitrogen oxide, that radical is also responsible for the depletion of ozone. So again, different reactants, different products, but same products, but all over same reaction, different reactants. So we're going to fly through this. And then we're going to look at past exam paper questions. So if I just get my OneNote open. Ah, yes, right. Zooming in. So what are hydrofluorocarbons? Well, they do exactly what they say in the tin. They are organic molecules that consists of chlorines, fluorines, and carbons. So what I'd like you to do is, I'm giving you two different types here, and I'd like you to pause the video and see if you can name them. We always need to, dust off our nomenclature skills. Very important. Okay, so if I look at this, I see that there is the parent chain is 1 carbon, methane. I see that there is 2 fluorines, difluoro, and 2 chlorines, dichloro. Now the numbering of the carbons here doesn't matter because we only have the 1. So, and when we name them, it's always alphabetically. So revealing dichloro, C before F, dichloromethane. Beside that, then we've got another sort of subset of chlorofluorocarbons. So the difference here is that there is a hydrogen. The hydrogen's present. So if you're going to give a guess, what are these going to be called? Hydrochlorofluorocarbons. So HCFCs, in other words. Okay. How do you guys get on with the naming of this one? So again, my parent chain is 2 carbons. It's going to be some kind of an ethane. I then have 1, 2, 3, 4 4 fluorines, tetrafluorine. Tetrafluoroethane. Okay, spot on. Same thing. So again, the numbering doesn't really matter here because either way, it'll still turn out the same. So no numbering, tetrafluoroethane will suffice quite nicely there. So these two molecules here, I suppose in the past, these CFCs were really popular, and we'll talk about that in a second. But because of their effect on the ozone layer, scientists, amazing scientists, have come up with an alternative that we use today called HCFCs. They're a lot safer, and again, down the line of this video, I'll explain why in a bit more detail. So, CFCs sound great. What's the problem? Well, back in the day anyway, when they weren't seen as a problem, they were very, very inert, so they weren't reactive. And why? So if you look here, the bonds between the carbon and the halogen, very, very stable, so they were very unreactive. As well as that, they were also non-toxic. That's always a plus. And they were also quite volatile. So CFCs are room temperature, or gases at room temperature anyway. But if I get, yeah. So in the 70s, if you had like a spray, CFCs would also be a propellant in aerosols. So that's what they were used for as well. They were also used as refrigerants. So they'd have a little, I suppose, chemical in the corner somewhere of the fridge, and they would be responsible for sort of keeping that cooling temperature. And they were also used as fire extinguishers. So they were really, really good at smothering flames. And as well as that, they were also inert, because we know like combustion reactions, smoke and flames, and that can be very, very tedious to deal with. So it was quite a plus that it was very, very good at smothering them and not being reactive. Okay, so again, I've talked very positively about them. So what is the problem? So if you go down here, so when CFCs are sprayed, or it goes into the atmosphere, and it rises and rises and rises to a specific layer around the Earth. And if I get this to work for me, come on. So if I go over here, so we'll deal with that equation in a bit. So it rises and rises and rises. Does anybody know the name of the layer? And it's about here, where it's about 20 kilometers to 50 kilometers up, if you know what it's called. So that's actually called the stratosphere. I'm just going to put strat for short. That's the stratosphere. And in the stratosphere, these chlorofluorocarbons are going to be exposed to UV light. So in the stratosphere, we are exposed to UV light here. So I've given a sort of reaction here of the product on this end and the reactants, no, the reactant on this end and the products here. Can you draw an equation using this in the presence of UV light? What would you put down? How would you write it out? So just take a pause and have a go with that. So when they rise up, they're in the stratosphere exposed to UV light. UV light, so we know that this straight bond here isn't actually straight in nature. We know bonds contain energy. These are always vibrating. Even me holding this pencil right now, the molecules in here are vibrating. I just can't feel it, but they are vibrating because it's got energy. UV light radiation, also a form of energy, is going to come down, and it's going to get absorbed by the CCl bond, and that's going to break it. It's going to give it so much energy that it's going to vibrate out of control until it breaks. And when it breaks, something happens. So the bond pair that would have been here in this covalent bond, one electron is going to go here, and the other electron is going to go here. And there is a name for when that electron, one electron, goes to each of the atoms. They're treated equally. What is that called? Do you remember? Homolytic fission. So homo meaning the same, the atoms are treated the exact same, the same number of electrons are going to each atom. Lytic and fission means like to break and split. So after that then, it's split up and we form what we call a very reactive species called radicals. We form two radicals here. And radicals are very, 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 very reactive because of that unpaired electron it's now possessing. So that unpaired electron is always represented by a dot. Okay, radical here, radical here. Aha, we meet again, chlorine radical. Right. Okay, so again, looking at this, you should be familiar with this very, very specific step in a free radical substitution reaction mechanism, where we have a very, very stable molecule that has been broken up by UV light and split into two radicals. What's that called again? It's called initiation, the very first step of that also important mechanism. So about this ozone, what's so great about it? So if I just scroll here. Right, so here we have our ozone layer, and within our stratosphere, our ozone resides in around here. and ozone is denoted, or the equation for that is O3. You don't need to know this, but it's formed quite naturally where you've got an oxygen radical and an O2, and they combine together to form O3. So within the stratospheric layer, there is a layer of O3, and O3 protects us by filtering UV light. Very, very, very important. What about this UV light? So there are 3 different types, A, B, and C. A being the, I suppose, not dangerous at all, and C being extremely fatal. So green, we'll just color code them of their threat. There we go. Right. So UVA. So UVA has the lowest energy, and it actually doesn't get absorbed at all by the ozone. It goes straight through, and it doesn't pose any health risk to us. UVB, on the other hand, does. So prolonged exposure of this UVB light. Now this does get absorbed a bit by the ozone layer. And if we're exposed to this for a very, very long time, it's going to cause genetic damage to allow for the cellular mutation. So when the UVB is prevalent, we know that, I should put A up here, that cancer is going to sort of accelerate. So a cancerino is when these sort of deformed cells keep multiplying uncontrollably. So that's an example here. Skincare, in Ireland anyway, it's definitely quite prevalent, even though we don't get any sun, but still UV light is there. It also, something very awful as well, it causes something called cataracts. So cataracts. And cataracts is basically where a cloudy, your lens on the inside gets clouded, and it obviously decreases your sight. You can even go blind, which is not pleasant at all. So, you know, wear sunglasses and wear sun cream, please. Cataracts. Now, last but not least, UVC. Don't need to write too much about this one, but UVC is the most fatal. It gets completely absorbed by the ozone, and more or less it just accelerates what happens here by a lot. And just, I suppose, for you, like whoever does physics, interestingly enough, you might know, I suppose, what makes UVA UVA, what makes UVC UVC. Well, UVA, it's all to do with when something is a form of energy, you know, comes in a wave. UVA has less energy, so the wavelength is a lot sort of flatter. And then when we have the likes of UVB and C, it's made up of lots of energy, so you see that sort of length quite a lot steeper, you know. So so we're going to look at what happens. So when the CFCs are broken up and we've got those chlorine radicals, the chlorine radicals then are produced by home electric fission, catalyze the decomposition of the O3 molecules. So we're actually going to look at that reaction now, and again, always our trusty bond enthalpy information. So see if I can zoom in here. I can. Right. So first of all, do you know what? Why don't you just give it a go? If you want to put a propagation step and how a chlorine radical reacts with O3, just have a go. If you get it wrong, get it wrong. Just have a go. Right. So the first propagation step. So again, I'm going to denote propagation P1. Okay. We know we're going to have a molecule, a very stable molecule, and a very reactive radical. So the first one is going to be the Cl radical. There we go. Don't give too much away there. So we see here our Cl radical is going to react with our O3. And what happens is it's going to sort of grab one of the O's from here. And what we do is we form this ClO, or chlorine monoxide. ClO is fine. ClO radical and an O2 molecule. So straight away, we've broken down in our propagation 1 step, we've broken down an ozone and have converted it to sort of an O2. So again, propagation 1, radical, stable molecule, making a new radical and a new stable molecule. But we know the party's not over yet, because we have a propagation step 2. Propagation always comes in twos. Right, so propagation 2, what happens? Do you remember what may happen? Right. So we know that we've got a new reactive species now that kind of wants a bit of the action. So we pop it down here. This should be a radical. So that's a one paired electron. So the CLO, or the chlorine monoxide radical, is going to react with more ozone in the atmosphere. It's going to go back and attack the ozone. And what that will do here is it's going to form a chlorine radical as well as two O2 molecules. And how does that happen? So the oxygen here is actually going to grab one oxygen from the O3. So if I can illustrate this, I wonder. So an oxygen here, I'm going to do that blue, we've got O3, okay? And it's going to knock off one of the oxygens to make O2. Okay, and then the O3 is left with two oxygens there. So we see, sorry, no, very slow. We see where the 2O2 comes from. And as well as that, I mean, if you look from right to left, you want to balance it out and it works out that way, okay? So again, we have a radical, molecule, new radical, new molecule. So the chlorine, again, in propagation, radicals are used and regenerated. It catalyzes the decomposition of ozone, okay? Breaking it down. Now, what was it going? Oh yeah, so why do I have the bond enthalpy table? So explaining this little step here as to why, I suppose the oxygen, like why doesn't this react with this, etc. Why does the oxygen go for the O3? Well, again, we know that if given the opportunity to be stable, if species are given that opportunity, it'll want to form the strongest bond it can, so it can be as stable as it can. So that oxygen is going to bond to another oxygen, because look at the size of that energy. It's actually the biggest one we've come across, 498. So it's going to readily form an O2 bond if it can. So it does. And then we also need to know the overall reaction. Where's this door actually? My cat opening and closing doors. All right, so we're going to look at the overall reaction. So if I wanted to cancel all the noise, so if I just get this red pen here, so if I get rid of the chlorine here, get rid of this, and just leave the O2s, ultimately, I'm going to have two ozones making three O2s. So that's what we call the overall reaction. Ah, it's gone. Oh yeah, I was going to write, I was supposed to write it down. Sorry. So two, bear with me guys. So 2O3 makes 3O2. And that's how holes happen in the ozone. Well, one of a few reasons, but that's one of the reactions there, okay? So you need to know the overall equation as well as the propagation steps here. You need to know this in particular, and hopefully I've illustrated that okay. So there's also another radical that causes the depletion of ozone, and that's our nitrous oxide. So I do need a little bit of space for this because I want to show you the reasons as to why this happens. So, right. So nitrous oxide. So again, we've got a nitrogen oxide radical reacting with an ozone molecule, making another radical and another stable molecule. But where does this NO come from? Well, there's a few places. So I would say it comes, we're going to deal with a combustion engine. So we know those cars, I can do a combustion engine here, right? A combustion engine from a car. Right, and we know a combustion engine of a car. I'm going to actually move this over here. It's going to get loads of attention. And we've got the smoke coming out, okay, and there's a lot of harmful products happen here. And what we can form from it. Okay, so we can form carbon dioxide, we can form sulfur dioxide. And the sulfur happens, if you remember, you know, the fuel that's in the car and that has impurities. So if you remember when we looked at alkanes, we looked at, you know, the combustion reactions and all the pollutants. So SO2 happens from sulfur, like these impurities from the fuel. We can also make water as well. And as a funny byproduct, this combustion engine is going to heat up an awful lot. And this heat, I might just do heat, this heat is going to force the nitrogen in the air, N2, to react with the oxygen in the air, okay? And it's going to make NOx, so X meaning it can have a range of oxygens. And long story short, one of those possibilities is that nitrogen oxide radical here. So hopefully that made a little bit of sense. I mean, we have to know this anyway for alkanes and stuff, but again, how the nitrogen oxides are made. Heat, very lots and lots of heat from the combustion engine, fusing these two together to make an NO radical. Right, so very similar to the last step. Radical is going to grab one of the oxygens and it's going to form NO2 here, and then we have our O2 that's left from the ozone there. Gosh, my brain went there for a second. Party's not over yet. What's going to happen? So this is P1. Propagation always comes in pairs. So we still have a radical that wants to get in the action, our NO2 radical. Dun, dun, dun. Right. Oh, this is going to pop down here. It's going to react now. I suppose note a difference. I have to note a difference here. The only difference is in this propagation 2 step, the radical reacts with another ozone. In the bottom one here, apologies, this radical is going to react with just an oxygen in the air. So I suppose in the air we're going to have an O2, we're going to have O3, we're also going to have like O as well, lots of different pieces, different bits and pieces. The NO2 is going to react with an oxygen, okay? And what's going to happen here is that one of the O2s is going to latch on to this oxygen in the atmosphere, okay? So then we get a nitrogen oxide radical as well as an O2. So if you were going to drown out the noise and get rid of this N, get rid of these over here, ultimately, what would the overall reaction be? Can you have a guess? 3, 2, 1. Overall, we have an O3 plus an O to make 2 O2. So an O3 plus an O to make 2 of these. So same reaction mechanism as above. The only difference is, I suppose, just to note that when the radical comes down to propagation 2, it's going to react with an oxygen. And again, it's to do with bond enthalpy, etc. Okay, just I suppose a matter of memorizing and knowing the steps. So that's all about the mechanisms. What I'd like to do is, before I move on, is talk a little bit about how these CFCs became banned. So scientists notice a hole in the ozone. I think I should have a picture somewhere. I think I do. So this picture was taken in 2006. So this is when I was in secondary school. I was in what we call, I think, second year. So second year is like your version of year 8, I think. So the biggest thing was, I suppose, global warming was still an issue, but the biggest scare at the time was there's huge holes in the ozone. Oh my gosh, huge holes in the ozone. And this here, we see the how the darker it is, that's like a huge hole. And that's because of those free radical substitution reaction mechanisms, okay? The O3 is being depleted, making like all those O2s, etc. So what happened was in the 70s and 80s, I think in 1987, there was this Montreal Protocol. And what happened is that scientists from all around the globe were working on this problem, and they had enough evidence to kind of push through this legislation and to ban CFCs. And so CFCs were gone out of refrigerants, they were gone out of all products that could possibly carry a CFC, were banned. And because of the magic of science, they did manage to find a replacement. So if you remember that CFCs, the hydrofluorochlorocarbons. Where is it? I think it's up here. So the reason why these are considered a little bit safer, again, you don't need to know it, but I think you probably want to know it, is I suppose it's a little bit more reactive in that even before it gets up to the stratosphere, it completely breaks down. So it doesn't get exposed to any UV light because it's completely taken apart by then. So that's what makes it a bit safer, FYI. So yeah, and what's actually absolutely brilliant, this is really topical right now because on the 24th of April, this big hole here has closed up. Like, amazing. I remember this being a huge problem when I was really, really young. So that's closed up now. And there is an argument. Some people are saying, oh, it's because of the lockdown and, you know, it's these restrictions. Well, funnily enough, it was improving a lot. Even in 2017, it had closed a significant amount. And I would argue that, yeah, I would agree, I should say, with the scientists in that it's not just because of the lockdown, because of these bans of CFCs over years and years and years. It was just the timing with the lockdown. It's now eventually closed. There is obviously still holes, but yeah, it's really, really interesting, I think. So what we're going to do now is I think we're going to look at some past exam papers, okay, and hopefully condense all this together. So yeah, I have a nice little sentence here that kind of summarizes my babbling. So research by different groups in the scientific community provided evidence for legislation to ban the use of CFCs as solvents and refrigerants. This has led to replacement by safer chlorine-free compounds and HCFCs. So let's go to our past exam paper questions. So take a breather, have a bit of a cup of tea, and have a pause and see if you can do the first question. So which molecule is not produced when ethane reacts with bromine in presence of ultraviolet light? So if you really know your free radical substitution reaction mechanisms, you can look at this and you'll know straight away. If you don't, sometimes if in doubt, draw it or write it out over it. So if you haven't got it straight away, I would just go back to basics with reaction mechanisms. So we know that in this case, it's mentioning bromine. We've dealt with chlorines, but I have mentioned in the past that bromine also is able to get broken up by ultraviolet light. So we've got Br and Br2 are bromine molecule, and it's broken up into 2 bromine radicals. And these radicals then like to wreak a bit of havoc. And what they do is they're going to react with, oh, come on, an ethane, right? So one of our BRs, so Br, we're on propagation now, Br radical, is going to react with an ethane. So I'm going to get in the habit of drawing the structural formula of ethane, CH3, CH3. Please, again, I always say, just see if you can beat me. I'm drawing via mousepad with a finger, so do, if you can, go ahead, please try and go ahead of me. Right. So again, we know that the bromine is going to grab a hydrogen because bond enthalpy, remember, and we're going to form molecule, radical, molecule. It's always good practice. I mean, that's the thing with mechanisms. The more you do, the more you know. Just like muscle memory. And HBr, my trusty, oh, I have to go back and HBr. And this guy is going to be my radical. So straight away, it's not going to be HBr because I formed that. All right. We know propagation step 2. So I might just, rather than drawing that out, I should be able to just cut it and paste it. So maybe not. Oh, goodness. All right, I'm going to draw it out. It's going to stress me out. All right. CH3, CH2, radical. And what's it going to react with? Propagation step 2, we dealt with chlorine in the last one. It's going to deal with the bromine molecule in the atmosphere this time. Okay. And it's going to grab one of the bromines. And I'm going to make CH3, CH2, Br, and a bromine radical. As always, propagation will form and regenerate our radicals. So I'm going to use this to indicate the products we've made. So I've made HBr. I have also made, see this over here? This is the structural formula of what? Which one is it? Oh gosh. No? It's this one. Okay, so that's a product, that's a product. So in termination, we know that we always produce two radicals. So in this case, we've got this radical here, and we've got this, we've got this, sorry, I'll just indicate it. We've got this radical here and this radical here. If I form two of these ethyl radicals, I'm going to make bromine. Okay? Bromine, I should say. No. Gosh, my brain at the moment. Methane. Butane. Butane. Sorry, butane. So I'm going to make butane. So I've made this with two of these. So the answer is going to be H. Right? Ta-da. Now, if you're really, really good at these, you don't even need to go through all that. You just know by looking, you know that a H2 is going to be formed. But those of you that may be still struggling, I'm just going to go through it as well. Why not? Practice makes perfect. Right. Oh, lovely. More nomenclature. No. Right. The compound 2,3,3 tetrafluoropropene is the refrigerant used in all new car air conditioners. Draw the displayed formula for this, pretty much. So ene means what type of organic member is it going to be? It's going to be an alkene. So as always, I'm going to start off with the parent chain. The parent chain is propene, which means it's going to have how many carbons? Zoom in here, I think. Pause, have a go, please. Learn by doing when it comes to organic, that's for sure. Right, so if it's propene, it's going to be 1, 2, 3 carbons. Savage, we've done this. It's propene though, so there's going to be a double bond somewhere, and if something has a double bond, it's going to be an unsaturated compound. Now, there's no number here. It's not prop 2-ene or it's not prop 3-ene, so it's safe to say that it's going to be on the first carbon. Either way, the numbering of that doesn't particularly matter here, because there's 3, so either way, it will still work out. So I'm just going to throw it here. So I've done my propene. My propene part is done. So now I want to look at my fluoro. So I've got tetrafluoro. I've got 4 fluorines around here somewhere. And that's going to tell me, these numbers here are going to tell me which carbon these 4 fluorines are on. So I've got 1, 2, 3. I've got 3 fluorines on the 3rd carbon. All right, so my numbering, obviously, this is going to be my number 1 carbon, number 2, number 3. Priority of this bond allows it goes from right to left here. So on my 3rd carbon, I'm going to have 1, 2, 3 fluorines. I encourage you to just go ahead of me here and, and I've also got a fluorine on the 2nd carbon. So here I've got a fluorine too. So I've done it. Well, not quite yet. I also have to have my hydrogens. So yeah, remember as well, and I assessed a few of your halogen alkane tests, and people keep forgetting to put hydrogens on, especially when it comes to like a propene or a double bond. Just remember that a carbon always is bonded to 4 things. All right, it's always got 4 bonds. Please don't forget that, because very, very easily Ross marks there. That's not necessary. So this carbon is going to have 1, 2, 3, 4 bonds. I'm going to add in my hydrogens. This carbon is going to have 1, 2, 3, 4, satisfied. This carbon is going to have 1, 2, 3, 4, satisfied as well. So perfect, that's it. The next one. Right, give one reason why 2,3,3,3 tetrafluoropropene is a more environmentally acceptable refrigerant than chlorodifluoromethane. have a pause and have a think. I'm gonna actually type this one out if I can. Yeah, got a hand here. Any suggestions? Well, if you think about it, what causes that damage in the environment? What is the culprit regarding the ozone depletion? So it's that chlorine molecule, isn't it? Or that nitrogen oxide molecule, but it's that chlorine one. So this contains the chlorine. This guy doesn't contain any chlorine. And we know that fluorines won't get broken up by UV light. Do you remember why? It's got a really, really strong bond. That bond delta enthalpy is quite large. Do you remember the reason why? Again, it's based on the size of the molecule. So fluorine is very, very small. So that lone pair that's shared between the two fluorines has a really, really strong attraction between that lone pair and the nucleus of the fluorine. Really strong, really, really strong, really, really small, way more energy needed, more energy than UV light could possibly have to break it. So it's quite stable. Anyway, on the other hand, chlorine isn't. So what I would say here is that does not contain chlorine. Or you could say does not release a chlorine radical as well. That's probably a nicer way. Does not release a chlorine radical. Now this is worth 1 mark. Either of these is completely fine. It's just looking for not too much detail. Does not contain chlorine, first of all. If it doesn't contain chlorine, it does not release a chlorine radical. Either of these is just fine. Right. Next one. Aha, so our nitrogen oxide comes in. Right, so the overall equation of our nitrogen oxide. Write the overall equation for this decomposition. So nitrogen monoxide catalyzes the decomposition of ozone into nitrogen. Oxygen. Write the overall equation for this decomposition. You need to know your overall equations. And what I mean by the overall equations, if you're going to take away all the noise of those propagation steps, what are you left with regarding the oxygens? It's going to be your O3. Oh, come on. Plus my oxygen by itself. Okay. And what does that make? 2 O2s, as far as I remember. Come on. Yeah. So again, just to verify that going up to the top here. Overall, right, cancelling out the noise. Same as this one. Overall for the chlorine one. Okay, don't forget it. Dun, 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 dun. Right. So that's that mark got. Well done, guys. I think it's worth 1, isn't it? No, it's gone. I think it's definitely worth 1. Right. Use the overall equation. Overall equation. We've just seen there. The overall equation to deduce step 3 in the following mechanism that shows how nitrogen monoxide catalyzes this decomposition. So overall, we have molecule. Now they should be showing radicals here. They should be showing. So what should be here is a radical, and what should be here is a radical. By the way, that's definitely the case. So again, radical, molecule, new radical, new molecule. It's a propagation 1. So we're basically just drawing the propagation 2 step for this. So propagation 2 goes down here, and we know that NO2 radical. What does it react with? The difference between this and the chlorine radical 1, just the 1 oxygen in the atmosphere, and we're going to make an NO radical plus, oh gosh, it's all going down here, plus an O2. There we go. Right, hopefully, yeah, you can kind of see that. And that's that done. Bam, marks got. Scrolling down a bit more. Okay, so bromine containing and chlorine containing organic compounds may have a role in the decomposition of ozone in the upper atmosphere. Draw an appropriate displayed formula, very specifically, in the space provided to complete the following equation to show how CbRF3 may produce bromine atoms in the upper atmosphere. So you're going to draw the displayed, which means you show every bond that's involved, all right? So have a pause and see if you can get that. What's happening here? Displayed. So we've got a molecule that's going to be split up into two radicals. This step is called our initiation, right? So UV light comes in, dun, 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 breaks this bond. Yeah, it does. And we're going to make our CF3. And just throw those bonds there. And again, it's not a radical unless you show that unpaired electron. And that's that one mark. Gosh. Okay, nothing too complex there. Lovely. Now, this is the last, no, it's not the last one. So in the upper atmosphere, it is more likely for CbRF3 to produce bromine atoms than it is for CClF3 to produce chlorine atoms. Suggest one reason for this. Now, thinking back to the last video, I'll give you a hint. Very thirsty. While you answer that, I'm taking a sip. Okay. So for this to sort of produce those bromine atoms and this to produce the chlorine atoms, the reason being is that the bond enthalpy, if you remember how much energy it takes to break a bond, so it's going to take, oh, and if you remember the trend for that, so there is a trend of bond enthalpy. I'm going to, yeah, I'll just do it here, right? So I've got my fluorine at the top, followed by my chlorine, bromine, iodine, etc. And there's a trend with bond enthalpy, which means it actually decreases going down the group. So bond enthalpy decreases going down the group. And there's a reason for that, to do with the size. Fluorine to chlorine, this gets bigger, this is even bigger. So there isn't as strong of an attraction between the lone pair and the nucleus. So it's going to take a lot less energy to break it off. So, what did I say for this? Come on. Zoom up, lovely. So I'll type this up. So I would say that CbRF3 has a lower bond enthalpy than CClF3. Okay, that's it. It's only worth 1 mark. They're not looking for too much more. So I hope that made sense. So if you know your bond enthalpies, you'll know that this guy is more likely to be broken off and to form that than this. I know chlorine radicals do form, but bromine will more readily be produced, okay, because of the bond enthalpy. Oh yeah, so this is the second last one. State what the dot represents in Cl. It represents an unpaired electron. We know that one. Lovely easy mark there. That's also 1 mark. And the last one then. Yes. So again, I always found, looking back at past exam papers, that they ask a lot of nomenclature-based questions when it comes to chlorofluorocarbons and all that. So it's a trend I've kind of seen. The compound 1,2-dibromo-1122 tetrafluoroethane is used in some fire extinguishers. Suggest the structure of this compound. Suggest the structure of this compound. So that's an interesting one. So again, starting from the last to the first, I look at the parent chain. Parent chain is an ethane, so it's going to have 1, 2 carbons. It's not going to contain, it's only going to contain single bonds because it's ethane, not ene. It's also telling me that there's tetrafluoro, that there's 4 fluorines involved in this compound. And those 4 fluorines are dispersed amongst the second and first carbon. So it's saying 2, 2, 1, 1. So there's 2 fluorines in the second carbon and 2 fluorines in the first carbon. Beautiful. So 1, 2, 1, 2. So fluorine, fluorine, Maureen, please work ahead of me if you can. I'm trying my best with what I have to work with. Okay, it's also telling me there's dibromo, so there's going to be 2 bromines, and these 2 bromines are going to be dispersed amongst the 2nd and 1st carbon. So I'm going to throw a bromine here, and I'm going to throw a bromine here. And that's it, a very, very well, simplistic enough structure for a very complex name up here, okay? So those are sort of the types of questions I've been coming across a lot. I've put up the ones that are sort of common. Also, they will, similarly to this nitrogen oxide one, they are going to ask for this here as well, okay? So just knowing the steps involved here, they'll pretty much be similar. But other than that, I hope it was of some help. Again, I encourage you after this video to ask me questions, whether it's via email or if it's via OneNote, you know, any stage. Just ask, reference, I suppose, the time of the content that you don't understand, and I'll get back to you as soon as I can and answer it as best as I can. So I hope that's helpful. Congratulations, we finished free radical substitution reactions, and we're going to be moving on to the nucleophilic substitution reactions. They're always a hoot. So I hope that was a lot of help. It's Friday. I'm mental because it's Friday evening and I'm making a video, but enjoy your weekend and I will chat to you very soon, okay? Right.